The fingerprint theorem, our book doesn't call it the fingerprint theorem, but does use the phrase that it acts like a fingerprint. In essence, if two random variables have the same moment generating function over some interval centered on 0, how big of an interval? It can be arbitrarily small. That means not that x equals y, but that they have the same distribution. X and y have the same distribution. So the moment generating function acts like a fingerprint, identifying the distribution. It's like, you know, what distribution do you have, X? Let me take your fingerprint. What's your moment? Your fingerprint is the moment generating function. Put it down. I see that moment generating function is the moment generating function for a normal random variable with mean 17 and variance 36. I've identified you. Now you might wonder, how could you possibly apply this? We definitely can apply this, okay? The first application is to figuring out the distribution of, okay, let's say Z is a standard, it's going to be a standardization of a random variable X, where X is normal with mean, mu, and variance sigma squared. This is not X bar, so it's not what Dr. Wetzel was doing earlier, but it's similar, right? We're subtracting the mean and dividing by a standard deviation. No random sampling here. This is not statistics. I'm wondering what's the distribution of Z. Now you can do this calculation for any random variable X that has a finite mean, mu, and a finite standard deviation sigma. And you can call it Z if you want, but mostly reserve the letter Z for when X does have a normal distribution. We did see before, we saw way back in chapter 3, that the mean of Z is 0, and the variance of Z is 1. Just properties of expected values and variances back in chapter 3 allowed us to see that. What we don't know until now is that if X has a normal distribution, that Z also has a normal distribution. And you can figure it out with the moment generating function, the fingerprint theorem. We want to try to compute the moment generating function of Z and apply the fingerprint theorem. Evidently, if that's going to happen, this moment generating function better be the moment generating function for a normal random variable with mean 0 and variance 1. That better happen. Kind of mysterious how it's going to happen. Start with the definition of the moment generating function. Expected value of e to the tz, right? That's the definition. You remember that, or have you forgotten? It's the definition. You use that even on an exam. I think this came up. All right, what does z equal? It equals that. I guess I need to use that, right? I'm assuming this. I better use that in some way. So I guess I should probably try replacing z with x minus mu over sigma. Oh, this is one of these things where that seems like a fairly obvious step, but then you just stare at it. It's like, well, what do I do with that? Well, we could simplify a little bit. I guess we could multiply the t through and maybe separate it. Maybe this is a good idea, maybe not. T over sigma times capital X minus T over sigma times mu. Stare at that for a while. Go get a cup of coffee. Stare at it some more. And then say, oh, wait a minute. Whenever I have e to the sum or difference of things, it's almost always a good idea to use properties of exponents. Another reason to learn it back in 8th grade. This is almost always a good idea, right? Whenever you're trying to derive something significant. Okay, I guess that feels good to do that, but where do you go from there? Get some more coffee, maybe take a nap, come back. What can I do with this? X is a random variable. What are these other symbols? T, sigma, mu, they're all numbers. I guess this is a number, a constant random variable if you prefer, but we could just think of it as a number. Oh, that could be factored out in the front. That's maybe a good idea. Is this a good idea or not? Do have a plain X there by itself next to this T over sigma. If that were just a T instead of a T over sigma, this would be the moment generating function for X, right? Oh, what do you do about that sigma though? Well, you can still use the moment generating function for X, just replace T with T over sigma. Now it feels like we're getting somewhere, right? Now what? Oh, I'm assuming X is normal with mean mu and variance sigma squared. Moment generating function for X. I can look that up in the table, right? Chapter 4. I purposely tried to memorize it before I came to class today because I was afraid I was going to forget it. E to the mu times T in general, but we replace T with T over sigma, plus sigma squared T squared over 2, but replace T with T over sigma. You can look that up. I'm using the fact that the moment generating function of X of T is e to the mu T plus sigma squared T squared over 2. That's the moment generating function for a normal random variable with mean mu and variance sigma squared. You can look it up. If you don't believe it, you can try to derive it yourself. Oh, 2e's, maybe I should go backwards now. Maybe I should add these exponents. Okay, I'll skip a couple steps here. I'll go ahead and slash right there. And I'm dividing by sigma really ultimately squared here, canceling with that. E to the T squared over 2, it simplifies a lot. Compare these two things. This is the general moment generating function for a normal random variable with mean mu and variance sigma squared. I'm saying the moment generating function of Z is this. These two things will be equal if mu is 0 and sigma squared is 1. Fingerprint theorem implies that Z is normally distributed with mean 0 and variance 1, which I'll write as 1 squared. We're done. Z does have a normal distribution. FPT means fingerprint. Yeah, let's do that next. That sounds like a good idea. If X is normal with mean mu and variance sigma squared, and Y is, oh, I forgot what the order they do it in, maybe alpha plus beta X. I don't remember if the book writes it like that or if they write it as beta plus alpha X. Alpha and beta are constants. And they have nothing to do with a gamma distribution. I might wonder, what is the distribution of Y? Let's see if we can do it. Let's see if we can figure out the moment generating function of Y. First, again, use the definition. And we're really just generalizing what we did in the previous example here. Replace Y with alpha plus beta X. See if I can do this quickly. Oh, I switched around where I put the T, but that's not a real big deal. That's a constant. It can go out in front. E to the alpha t, expected value of, e to the t beta x, e to the alpha t. This is the moment generating function of x. Okay, now I'll write it as beta times t. But x is normally distributed. With mean mu and variance sigma squared. Stop me if I make a mistake here. Now add the exponents. Combine those two and factor out a t. Get alpha plus mu beta t. And with this one, probably seems best to write it as beta times sigma squared t squared over 2. Which is the MGF, the moment generating function, for a normal random variable with this mean and this variance. Look good, no mistakes there. Normal. I'm being inconsistent in where I put things. Recall x had this distribution and y was alpha plus beta times x. So when y is a linear function of a normal random variable like this, y is also normal with mean equal to alpha plus beta mu. It's effectively using the same equation and replacing x with its mean to get this mean. And variance equal to the square of beta squared times the variance of x. Which makes sense based on chapter 3, right? Yeah, we knew that from chapter 3. The only thing new is it being normal. We knew this in chapter 3. And by properties of variances, constant random variables are independent of any other random variable. So I can write that the variance of the sum is the sum of the variances. Thinking of alpha as a constant random variable, it's going to be independent with beta times x. They're unrelated because alpha always equals alpha. Alpha being constant, its variance is going to be 0. And a property of variances here is that you can factor the beta out as long as you square it. So that's what we knew back in chapter 3. Verifying that we have the right mean and the right variance. Again, what's new here is now we can say y is also normal if x is normal. So it's still worth doing, confirming that the distribution is normal.